Welcome again. This is it. This is week 11. We will begin with chapter 6, the first part on perception and cognition. And this is one of the most complex chapters in the textbook that will require some basic knowledge of mathematical modeling, mathematical theory, some basic mathematical terminology. In the context of understanding logical processes, proofs, and theorems. So please bear with me. In this week you will see again less and less of me because you don't really need to see me. You will need to see equations, demonstrations, and certain patterns you need to recognize. So we will begin by examining what mathematical thinking is and why is it so important in the context of critical neuroscience. Well, this has to do with perceiving, sensing, evidencing, understanding, rationalizing, constructing, demonstrating, analyzing, and many other processes that are by definition cognitive, but they're also computational. So in this week there will be a little less room for, I would say, transcendental speculation per se, despite the fact that there will be a few things borrowed from abstract mathematics. But I hope that you will use the knowledge that you will gain this week to reconstruct some of the assumptions that we made in the previous weeks. So now that you have both the theoretical knowledge, you have the external framework, and now you will add some ingredients that will, to some extent, become the new building blocks for all the arguments you had for or against a dualistic or monistic perspective in regard to the hard problem of consciousness. All right, now you might wonder, why does chapter 6 start with the mind-body problem, a general overview? You might think, well, wait a second, did we talk about the mind-body problem throughout the course? So why is there a need to go back and talk about it in chapter 6? What about the previous 5 chapters? And why a general overview? Didn't we discuss different perspectives quite in depth so far? Well, you'll be partially right. Because I feel we did a good job overall in providing evidence for this or that model. But what is still lacking is a solid mathematical, analytical, logical examination of each model. We did a good job in providing an overall pictorial, figurative, metaphorical comparative analysis of different views on the hard problem of consciousness, on the way the mind and the brain interact. But it is very important, before we move on to the very last big topic of this course, which will be indeed the triple S model, it will be important to have a solid mathematical, logical foundation for any of the claims we will make toward the end of this course. Now, will you have to work on some calculations during this chapter? Well, the answer is no. You will have to understand some of the very basic logical equations and demonstrations as part of this chapter, but by mathematics in this chapter we do not mean either calculus, algebra, geometry, engineering, or physics as applied mathematics. We mean mathematics as both logical processes and recognition of patterns. That's the way we will approach mathematics just in this chapter. So once you will have a solid grasp on basic mathematical premises and formulas, so very basic math terminology, then you should be able to navigate the content of this chapter quite easily. Now, this, by the way, might be a little too easy, too basic for the ones of you that might come from either mathematics, physics, engineering, or other STEM related fields. So bear with me if the introductory part to this chapter, it's not too profound for your current knowledge. I just feel they need to go back to the basics to make sure that the content of this chapter is accessible to all of you. So let's begin right away. Wonderful. In this section, we will be talking about mathematics. Mathematics as a field that has to do with recognition of patterns, and more specifically, mathematics as language. So the first thing I would like to mention here is that we will be talking about logic, more specifically, mathematical logic. Now, let's begin with an example even before we address some of the basic symbols in logic. So I have a little statement here with me on a piece of paper, and I will read it to you while I will show it to you. So the statement on the other side is false. That's the first premise, the first thing we know. Now we will turn around, flip this over, and the other statement says the statement on the other side is false. Now we already are encountering a problem because the first statement says something about what's on the other side and vice versa, albeit vice versa it's not a good term in this context. So what else can we say? Well, there is a confusion, there is a clash of statement because the statement is connected to the other one in a wrong way, we could say. Let's use that term for now. So if this statement says the statement on the other side is false, we cannot assume that what the other side says is actually true because this will clash with the premise. Now, let's see what will happen in another case where the beginning is the same, the statement on the other side is false, so we know, we are expecting that what we are about to read will not constitute truth, but if we turn this, now we have the statement on the other side is true. Now, this is a problem because there's a connection here that doesn't follow. Now, this again constitutes a paradox, and I mentioned a few weeks ago Kurt Gödel and the incompleteness problem. But as you can imagine here, the premise and the outcome are clashing. There's something that doesn't quite fit in our logical sequence. So one statement says the opposite of what the opposite actually is. So again, the statement on the other side is false means that what we are about to read on the other side cannot be taken as valid, cannot be taken as true. So when we turn around and it says the statement on the other side is true, it means that on the opposite side the claim was correct, so we cannot trust the fact that this one claims that the other one is true. So you see there is a continuous, never-ending logical sequence here that will create a problem in our understanding. And this has to do with, of course, the paradox on a logical sense and what really Kurt Gödel had to say about the incompleteness theory. But let's begin with some basic mathematical logical symbols, and then we will venture into some very, very basic equations. So we will be talking about statements, and we will be talking about properties. Now, of course, one of the important things to keep in mind is that we need to connect multiple statements and we need to define the type that is connected to any of the previously stated elements. Okay, so types. Now keep in mind what we said about the principle of falsifiability in previous lectures. So what are statements? Statements are sentences, and statements declare something. So let's keep this in mind. Statements have to do with declarations. Okay, so they declare, okay, which we can also say they clarify whether something is either true or false, okay? Or rather, to say it better, statements can be proven to be either true or false. So again, they follow a binary system. Okay, so beyond true and false statements, we also need to clarify the fact that there are statements and there are non-statements, okay? Now, in the context of mathematical logic, a good way to think about this is that certain statements are sentences that don't apply to our principle of falsifiability, so they are not constructed on a binary code. So questions are non-statements. For instance, can I use logic in the context of a question such as, do you think it will rain today? Well, this is constructed as a question, do you think it will rain today? So this will not be a statement from the perspective of mathematical logic. So, but let's use this as an example, because let's assume that we want to have a logical examination of the possibility that it might rain today, or something about the fact that it's going to be a rainy day. So let's just write here for a second, rain today, rain today with a question mark, okay? And then we will add something else. For instance, drive slowly, all right? So let's add something else now that is different. It's also a non-statement, okay? But it's not a question. Drive slowly, okay? So one of the ways to look at mathematical logic is verifying whether something can be proven to be true, and this has to do with mathematical proofs, and we have to connect, in this case, two statements. How are we going to do this? Well, the first thing to keep in mind is that we need to rearrange those statements to make it logical. Not logical because they are in themselves illogical outside of the sphere of mathematics, but we have to construct them in a way that we can use to verify based on the binary code we mentioned previously. So let's do that. So let's assign some letters to these two sentences. And again, this is not as relevant. I would not say that you have to pick specific letters necessarily, but it is really important to know that at least in mathematics there are certain agreement on which symbols to pick. There might be some variation between textbooks, but for now let's just assume that the green one is a statement P, okay, so this will be the letter we will assign to it. Let's use a capital P for now. And then the blue one will be, let's say, a Q, for instance. Okay, P and Q will be the two statements. Now again, we already mentioned these are non-statements from the perspective of logic, so let's recreate our analysis by changing the way they are semantically structured. So our P, okay, our P now will be today rains. Okay? So this is a statement in a logical sense. And our Q will be I drive slowly. Okay? Now, of course, there might be some more issues with this because using an adverb, okay, might constitute a problem in itself simply because it's predicated upon a how-ness rather than a 0 or 1 binary code. Okay? It would be much easier if it says today rains and I drive rather than I drive slowly, or rather this will require a further analysis from the logical perspective. So let's try to connect these two. Okay, so the first mathematical logical symbols that I want to present to you is the AND symbol. So if we sum up P and Q, we could say that today rains and I drive slowly will constitute this and. So today rains and I drive slowly. Okay? Let's try to convert this to something that actually is more logical from our perspective. So today rains is P, and I drive slowly is Q. Okay? So we can remove this now. Now, is and sufficient? Well, in general, in logic, we will not spell it out. We will use symbols such as this one, or this one. Okay? So all these three mean and. P and Q, P and Q, P and Q. Again, today rains and I drive slowly. Now, I would not advise you to use this one a lot because it's not it's too confusing, and obviously it does not apply only to mathematical logic. And of course, just FYI, this and symbols is a contraction of two symbols written in medieval Gothic alphabet, et in Latin, okay? And if you write et long enough, you will get this symbol. Okay, so it's just pretty much an et, which is Latin for and. Okay. The dot here could also be confusing because in some textbooks it's utilized for multiplication. So perhaps this is the symbol that I will use in this explanation, in this brief discussion. So to rephrase everything, at this point we will have P and Q, right? So P and Q, again, this symbol, just for clarity, is called either the caret, which is not something you eat, okay, C-A-R-E-T, or circumflex. In the first case, caret comes from carere, which is Latin for is lacking, is separated, and something that you will utilize in the context of amanuensis writing, for instance. For circumflex, we use this more in linguistics, especially to distinguish the length and type of a vowel. Okay. In Slavic languages, you might have the opposite, which is the opposite, the accento circumflesso rovesciato, we will be something like this, like the difference between the ch and the ch, for instance, okay? In Cyrillic, this one. So, and, or caret, or circumflex is the term, the logical symbol that we utilize to discuss this P and Q. All right, so this is uniting something, and it's a conjunction, so this is a type of statement that we define as such, and so each of these statements are simple statements, okay, but the and is a conjunction, okay, conjunction, okay, caret. Now there are of course other types of statements that will be linked in a different way. So if by conjunction we mean uniting together, and now of course we will have the disjunction, okay, disjunction, that is no longer an A, but it will be an or, okay? Now this or, it's the opposite of, well, it's the opposite aesthetically speaking. So it's the wedge or reverse caret, and it really looks like a V. So for instance, if you want to say, today rains, or, let me use the different color here. Today rains, or I drive slowly, okay. I would now write P wedge or reverse caret Q. So P or Q. Now, those are statements that are pretty basic, and one of the things that we want to keep in mind is that we need to figure out a way to demonstrate whether this is true also on the premise that independently P and Q are true. How are we going to do this? Now we need to identify a truth table. Now we will leave the philosophical discussion on what truth actually means in the context of mathematics in the next lecture. But for now, let's just see how this table actually works. So let's start with the and first. Let's start with the conjunction. Okay. So our assumption is that today it rains today, and I drive slowly are independent statements. So again, we'll write it here. Today rains. Today rains, and I drive slowly. Okay. Again, become P and Q. Okay. And now we'll see what happens with both conjunction and disjunction. So let's begin with the conjunction. Okay. So we have this element, this statement, okay? And then we have this element, okay? Let's do this. So, if P and Q is true, we will have to identify the truth for each of these statements. So let's remove the wedge here and just leave P and Q and create a third column here, okay, where P and Q are actually linked together by a conjunction, okay? Let's do this. So let's assume that P is true, okay? T. Today rains, it will rain, okay? Let's also assume that Q is true, okay? I drive slowly, so they are both true, and they are both true, so since there is a conjunction here, the conjunction itself will be true as well. What will happen if P is true, but Q is false? At this point, one is wrong, one is false, and the other is true. Therefore, this one does no longer hold true. So this will be false as well. Again, conjunction. Third possibility. P is false, but Q is true. Okay? Again, it is not true that today rains, okay? Or rather, today rains is a false statement, true, and I drive slowly is true. However, because of the conjunction, this will also be false, okay? Third element, fourth possibility, they are both false, and of course, since they are both false, this turns out to be false. Wonderful. So let's redo this. Okay. We'll recreate our table. Okay. But this time, rather than conjunction, we will use the disjunction. Okay. So again, the disjunction as the wedge. Okay. So same thing. P and Q, and then P or Q. Same thing. Wonderful. Okay, great. So let's use two different colors for clarity. So P is true, but Q is false. Okay? Since we're talking about either or, this turns out to be true. Either or. What is the opposite? If P is false, but Q is true. Same thing. We're talking about disjunction here, so this turns out to be true as well. I changed the order, of course, from the previous one, so let's assume that they are both true. Now, the wedge simply says that as long as one is true, you are all set, so to speak. So this will also be true. What if they're both false? Okay. Well, in this context, unfortunately, since at least one has to be true because of the disjunction, this statement turns out to be false. All right? And this is how you create a truth table for conjunction and now for disjunction. Now, of course, when we're talking about or, when we talk about disjunction, we should also specify the difference between sufficient and necessary as conditions. But we will do this a little later. So let's continue with some basic symbols, okay? And we will apply truth table to those symbols as well to verify the claim. So we can stick to these two examples here, okay? So again, we already mastered the first one. So the end is P and Q, okay? Then we followed up with the or, okay? And we wrote P or Q like this. Now, of course, we have two different types of or. One is inclusive and the other one is exclusive. So let's take a look at the symbols first. For the inclusive or, all right, we will have P or inclusive R. Okay, so either P or Q. My apologies. Either P or Q. Okay. Now, either P or Q, but since it's inclusive, it means that the way you create this sentence is either Q or P or both. So either P or Q or both. So that's the difference, okay? To be more specific. How about the exclusive or? So the exclusive or represents an exclusion so either P or Q, but not both. I'll just do it this way, okay? Okay? So this is an inclusion because it can be either or both, and this is an exclusion because it can be either or but not both at the same time. At the same time, not chronologically speaking, but simply logically speaking. Wonderful, but what if any of these letters actually are assumed to be a negation? What if it's an assumption that it's a not P or not Q, okay? Which is not the reverse, okay? We have to be careful here. So if you want to use a negation, we will use the term not, okay? So a negation is reversed truth value, okay? So to clarify, a negation is a simple statement, but it's a simple statement with a reverse truth value. Okay, so let's see how it looks. So simple statement, so and or. Now we'll do not right here. Okay, either you can write something like this, P, or you can write it like this. Okay, I prefer the second one, this one here, because this symbol here very often is used in different ways. Depending on what mathematical textbook you follow, I seen this one to infer similarity, and that is actually not correct from the perspective of logical mathematics, so I'll much rather use these symbols to say not P. For instance, not today rains, okay? Or not I drive slowly. Careful here, the fact that I put a not in front of it, it doesn't mean that I drive fast or faster, okay? It simply means that it's a negation, okay, of this statement, okay? And again, negation does not mean claiming that the statement itself is false, okay? So it's a not within simple statements. Okay, let's continue because we have a few more to discuss. All right, now we have, of course, those were all simple statements. Now we have conditional and biconditional statements. So within conditional, we can say that it's a statement that follows the if-then type of structure, and biconditional, as the name implies, it will be a statement that establishes a two-way truth between two-way truth relationship between the two statements. So let's make some room here, okay? So conditional is represented by the symbol either an arrow or horseshoe, okay? Whichever you prefer. So if P, then Q. Okay, so in the example above, if today rains, then I will drive slowly, which kind of makes sense intuitively in terms of the statement itself. Okay. Now, biconditional is represented by this symbol. So this one, or you can also use this one. Okay, great. So what do we use biconditional? Well, in the example above, if and only if okay. Now, I will drive slowly if and only if today rains. What about the opposite? Today it will rain if and only if I drive slowly. So you see already a more profound layer of interpretation, which also connects the statement to temporality. If you remember what we said about Heidegger and Hegel, that's where everything comes together. So the sequence itself is as important as the way we create our statements. Now, I forgot to mention that if and only if, very often it's written with double F's. So IFF, if and only if. This is another way to represent a biconditional statement. Okay, so there's a lot more to say about this relationship, but I want to give you a brief list of the mathematical symbols that we will utilize the most in logic. So let's start with one of the most commonly utilized, the symbol that almost defines equations in themselves. It's a symbol of equality, which is this one course, okay, equality, which of course means that it's equal to, okay, x equals y. Let's continue. How about if it's approximately equal? Well, you will use this wave-like symbol, okay? So approximately equal, okay? So for instance, x and y are almost equal. Now you might have seen these three lines here, okay? So similar to equality, but at this point we have the definition of the definition. So this symbol is utilized for definition, okay? And how are we going to read it? Well, x is defined as another name of y. Okay? And again, we're talking about statements here. So if you want to use P and Q or P and R or S and P for any of this rather than X and Y, that is perfectly fine. All right, what if this is an inequation? Well, as you would imagine, the symbol is like this, okay? And this is, of course, defined as such, inequation, okay? Which simply means that if X is not equal to Y, they do not represent the same thing, they do represent the same value. Fantastic, so let's continue. Now, the more than and less than, I feel it's something that is pretty straightforward, so we can skip that, or much less, much more than that, we can also skip that one. I would like to continue though with few or greater than, right? With the or smaller than, those are also pretty straightforward, but those are the ones, first four are the one that we are mostly interested in. And perhaps proportionality as well will be one of such terms that we need to use proportional to, okay? Because that is connected to the theory we'll be discussing. I mean, another one that I feel we should mention is congruence, okay? Whether something is congruent to, and this symbol is like this, okay? So congruence, okay? And congruence in this context means that if x is congruent to y, then shape x is congruent to shape y. So this has to do with measurements. Next, I would like to show you just the difference between these three symbols, because we will be utilizing that in the context of theory of perception and neuroscience. So one symbol is this one symbol is this one, and another symbol will be this one. Okay? Now these two both represent set membership, okay? So set membership. But this one means is a member of, and this one, as you'd imagine, is not a member of, okay? Okay, of this set. Now, what about the third one here? What about this symbol here? Well, this one means is a proper subset of. All right, so what's the difference between these two? Let's just make some room here. What's the difference between these two symbols? All right, well, this is only for one element, while this one is for a set, okay? Just keep this in mind. So again, it's very important to understand what we mean by certain symbols that are, as I mentioned, agreement upon which symbol to use. But if there's any uncertainty about what the symbol actually means, simply because you have different models, then please utilize the one that has less room for misinterpretation. So earlier I mentioned the tilde, right? The negation symbol, and I mentioned that you can use either this symbol here or this one. And by the way, the term tilde really comes from titulus, or titolo in Italian, okay? Which has to do with title, of course. But if these both represent negation, then I would prefer this, because this one also means similar to. And so this symbol in this other interpretation is connected to this symbol, okay? Which in turn is connected with this symbol and eventually with this symbol, okay? So this, of course, has nothing to do with negation in this context, and I'll be very, very careful in utilizing the tilde in this shape rather than in this shape for this very reason. All right, great. So some more comparisons here. Okay, a few more things regarding relations concerned with inclusions. So we mentioned a few of this, but I feel that we should specify a few more things. Okay, so let me add the comparison between these four symbols here. So in the first one, we see that every element of A is an element of B. Okay, so that's the first example here. Okay, every element of A is an element of B, which means that A is included in B, or A is a subset of B. Let's move on to the second one right here. So with this one, we mean that B includes A. Okay. All right. With this one, we mean that B includes A, or B is a superset of A. So look at the direction here. Okay. Again, if you remember what we said earlier about the arrow, so this one has this direction and this one has this direction. Please do not confuse this symbol with this symbol. Okay, we're talking about the arrow here. So you could say that this one, this annotation, okay, with this order, means this one with this annotation here in this order. Okay, great. So we talked about directions. So let's move on to the very last one, the last pair of these symbols. If we were to write something like this, what we really mean is that every element of A, okay, every element of A is an element of B, and there is an element of B that is not an element of A, which of course is connected to the broader utilization of the meaning of this symbol, okay, which is of course not AC. All right, starting with the hypothesis A1, let's visualize this one.
Now, we start from a reductionist equation, so to speak, and we will hypothetically assign the coefficient x and y,
okay,
to mind and matter, respectively. Now, of course, the main difference between the two hypotheses, the H model here, is whether these two variables are actually equal, not necessarily identical. Now, in the equations that we report here, this material equivalence presents two added aspects. A, it poses a biconditional logical connective in the second case between x and y, thus an if and only if carrying necessity and sufficiency. And B, it involves further investigation on the constants of valence versus value, again in propositional logical terms. This is connected again to Heidegger in relation to the essential being of matter versus mind. In other words, this if and only if presupposes at least two moments, either temporal, chronological, or spatial, between A, the observation on X, and spatial between the observation of Y, and 2, or B, between the first primary observation of x and y and the second secondary observation of x and y. So let's continue. We're talking about union of sets here. So in U2 we can see that a weak equivalence between x mind and y matter is united to a strong equivalence between these two variables, while in U3 we observe an intersection of these two levels of strengths. However, applying this significance in the context of consciousness would mean that the same order of magnitude found in this connection would account for an approximation based on logarithmic calculation, while the isomorphism defined its equivalency would mean that the mind and matter are structurally identical. Now, in all this union of sets, so U2, U3, U4A versus U4B, the idea is to define whether mind and matter are structurally identical. So to quantify matter, to see how mind and matter could be at least mathematically connected by computational relation, or in other words, via the analysis of computational balance, providing the same number for both entities. We talked about base 10 logarithm. Now, saying instead that mind and matter are structurally identical is actually going beyond their mathematical number, or that in a halomorphic sense, Heil and form present the same structure. To clarify, I do not expect students to remember these equations, but get a grasp on the general conversation how to demonstrate the connection between mind and matter.
Okay, great. So we need to verify the following. Okay, great. So
now, since we're talking about the realm of hypothesis here, we talked about mathematics, logics. The assumption here is that we can theoretically create a separation between x and y to verify the existence of such separation, which appears to be a contradiction in terms based on all the premises. Now, things are complicated by the fact that not only the separation might be an artificial one, but also that this artifice to obtain such results is created by the observer, by the decision maker, or by the observation/decision-making method, by the cutoff method. Thus, we should at least attempt to calculate the probability that each of these solutions might actually be close to truth, in a statistical approximation sense. So we could start, by verifying each of the hypotheses, the probability for each of the hypotheses, HA1, HA2, and HB, in the following way. So there are 5 different steps, 5 different ways. A, the probability of X, thus limiting the investigation of whether there is enough warrant for independence existence of mind. And my apologies, in the slide I mentioned that there is a misspell. It says ether rather than there. B, PRY, thus limiting the investigation of whether there is enough warrant for independence existence of matter. C, probability of HA1 for identity, structural, computational, etc. D, a probability of HA2 for material equivalence by conditional logical connectivity in terms of a necessity sufficient for existence, and the last probability for HB for equivalence as opposed to equality. Again, since we're talking about a possible comparison between computation and structure, again, Heil versus form, and probability p-value, it might be appropriate to remove or at least account for fixed significance thresholds as opposed to incremental values. This will mean interpreting our results as grades or degrees, as well as steps or stages of the strength of evidence of existence against a null hypothesis. We should at the same time be very careful in not assigning value to the value, mathematically speaking, given that our investigation is about the parameters which would help us define the existence of mind and matter as either completely separate entities, combined or interacting entities, or if we should only talk about one entity, interpreting with features appearing connected to a mind-body series of processes or activities, or a matter-based series of processes or activities. Again, in HC, the arrows are bidirectional, thus implying mutual implication between mind and matter. This view represents the core of dualism from this specific perspective, although to better define which type of dualism we're talking about, we suggest we operate a further split from this level to the secondary level. And again, talking about dualism, there's many that we previously discussed: substance dualism, predicate, property dualism, but also epiphenomenalism, interactionism, occasionalism, universalism, etc. And in the last part of this analysis, we compare again our table on page 158 and the theories that we mentioned regarding Kerner, McGinn, Taylor, Wolfram, also in connection to Ishikawa and in Ishikawa's perspective of linguistic limitation, in connection to worldview limits, measurements, and measure. And of course, the measure issue goes all the way back to the measurement axiom and the analysis of Ishikawa, of course, but also the analysis of Schrödinger, starting from the Hamiltonian operator H. Define the system's total energy, set spectrum of possible outcomes when there is a measurement, or the total energy of a system. To clarify, I do not expect students to remember these equations, but get a grasp on the general conversation how to demonstrate the connection between mind and matter. So you might wonder, what's the value in learning all these equations, despite the fact that, yet again, I'm not expecting you to memorize any of these equations. What's the value to better understand mind and body connection? Well, this chapter talks about perception and cognition, and I hope to have had the chance to indicate how our perceptual factors have a lot of connection with the way we interpret the world, the way we think about the world, cognition, and in turn, the way we think about the world influence the way those very things are entering the system, are being perceived by our system. And I mentioned the connection with the social cognitive theory and the model proposed by Bandura. You can find this on page 166 and 167. And this it's something that is related because we consider a three-dimensional conceptualization of the mind-body problem. And this triangle would immediately make us think of Trinitarian theories, especially in the metaphysical or even theological sense, when you think about the Trinity, but also in relation to the physical dimension of structural features, for instance, the double helix of the DNA. And you probably all know the work by Francis Collins, who focused on the human nature, on the divine origin of evolution, on the genetic substructure of creation, including humans, and on the moral law, yet again perceived by us humans. And in conclusion, a solid focus on altruism through the philosophical analysis at the basis of the research on the Human Genome Project. I will also like to mention specifically in regard to the conceptualization of the natural and moral law connection, the work by David Berlinski. Now, the most important aspect of this perspective is the presumed scientific requirement that science demands atheism from within. And in other words, science uses itself to claim that it's more scientific to expose a position in which there is no warrant for a God than the other way around. Collins, again, presents numerous fallacious assumptions of the concept of a deistic versus theistic and personal God or religion, and the same can be said about David Berlinski. What is the scientific research in terms of empirical studies? Well, there are plenty of research studies that and the phenomenon of connection between a transcendental nature have been analyzed by many scientists. I just want to mention yet again the work by Mario Beauregard on the alternate state of mind, by Moore, Janssen, Van Loon on near-death experiences, the model that we mentioned a few times on consciousness by Roger Penrose and Stuart Hameroff, the research by Stevenson on reincarnation, and many others. But of course, what is missing and what's truly transcendental, in my mind even spiritual and metaphysical, is the fact that none of these small parameters, relatively small parameters, well separated from each other, cannot create consciousness. So there must be something more that is equivalent to more than the sum of its parts. In this regard, I want to mention the quote on page 187. At the end of his scientific career, Penfield concluded that higher mental functions, such as consciousness, reasoning, imagination, and will, are not produced by the brain. Mind is a non-physical phenomenon interacting with the brain.
Wonderful. So we will stop here as far as mathematical logic. There are certainly more things to discuss, and we will continue our conversation. But for now, those are just the basic parameters that I want students to be more familiar with, also in order to understand the overall theoretical frameworks for this specific chapter, which is one of the most dense chapter in the textbook. So we will continue with the next topics. Thank you very much. This was a very complex series of topics. We just completed week 11 on chapter 6, Perception and Cognition. So we will continue with the second part of chapter 6, and we will move on to computational neuroscience, sensory neuroscience, and other elements within theory of perception. Again, I want to thank all of you for the attention, and I will see you next week. Bye-bye.